Hey, well, it's start time. Actually, it's a little past here, so better get you guys started here and just kind of remind you of where we are and where we're headed and a couple other announcements. Hopefully where we are and where we're headed is obvious because you've hopefully given it a lot of thought. If not, you're going to have a very, very busy 2 days here. But you've got a test coming up, and it's on our first 4 chapters. And as you know, and I've been saying, these first 3 chapters were quite significant in their materials, and so we've done some good chapters here on the first 3, some basic physics. Then we did this 4th one, chapter 26, where we I call this the practical side, the applied physics, the engineering chapter, where we learned about capacitors, and we mentioned at least one reason why we would use a capacitor. We did a lab on it where we charged up the capacitor and we used that to run a light bulb. And so we've been working with capacitors. What I haven't got a chance to do in chapter 26 is go through some example problems. So that's what I want to do today. Is I've got a long list of example problems, and so I just want to start doing some examples for you from chapter 26. And I know at this point, with the test coming up on Thursday, you've probably already been deeply diving into them, and I could tell by your questions and working with Don and what I see on the whiteboards as I walk around. I go, okay, obviously people have been working with that. So like I said, I just want to continue to do that, and that's the game plan for today. So examples from chapter 6, test on Thursday, chapters 23 through 26. A couple announcements, though. I'll start with the exam. Thursday exam, come early. And we're going to do the same kind of setup you saw last semester. Let me explain it again, especially for any of those who might be new. But what will be a little bit different is I won't actually be here. And so my son broke his lower braces, and so I got a dentist appointment all set up for him. And I could only arrange it in Thursday morning there. So Thursday morning at 9 o'clock, I'm going to take him over to the dentist. So you'll still have Don. You'll also get a chance to meet one of our night instructors, Dr. Kelly. So Dr. Kelly's going to be my substitute. I've been talking with him that the setup will be exactly like it was last semester, those of you who had me, and let me repeat it now here, but he'll be here. And so Don will be here too, of course, in the overflow room. And so we'll have the same traditional 3 rooms. Let me explain those. You guys in DSPS, you've got your DSPS room. I think you know where that is. Come at 8 o'clock. We'll get you guys started in there, or actually Don will get you started in there. I won't be there. So that'll be at 8 o'clock. The rest of you, starting at 9 o'clock, or actually I should say 5 to 9, come a few minutes early. Some of you are going to want to go into the overflow room, the PS116, and great, I encourage you. Don will be there just like before. We'll put 2 at each table. He'll have a bunch of tests, so if we could get about 30 people in there, that would be awesome. The rest of you will be in here. Dr. Kelly will be in here. Come early. Just like last time, he'll have one of those cards, you know, and you just come in and it'll be that same grid, right? This is row A, this is row B, C, D, E, and F. And so grab one and find out where your seat is. We'll put a map up here on the board. Now I'm trying to remember myself. Did we do 1 through 4? We did 1 on that side, 14 on that side. So A1 through A14, B1 through B14. Anyways, find your card, because then when he passes out the test, he will pass them out and they'll be marked. So make sure your test marks the seat you're on. And so he'll put one color here, pass it straight back, one color here, straight back, one color here, straight back, one color here, straight back. And then just confirm that the card you have matches the number on the test here, so that when I go to grade them, I use the right grading key with your test and your numbers match. And so I don't want to be marking it wrong just because it's the wrong grading key with the wrong color. And then you'll see me, I'm going to try and get here, well, as soon as I can, definitely, and that might be near the end here. Yeah. No Scantrons. Obviously, you'll need a calculator, but that's all you get is a calculator. The scratch paper, I'll just remind you, if you remember, whatever color of test you have, you should have matching scratch paper of that same color, and there'll be 2 sheets on the back there. So you can use the back of a test question, or you can just tear off those other 2 sheets and use those 2 sheets. If you need more than that, well, I'll have more up here. I'll give it to Dr. Kelly and to Don, and so just make have your scratch paper. All I ask is that your scratch paper matches the color of your test, so that there's no white paper out there being passed around and you don't know what color tests I'll be using. So make it a little more secure. Second big thing I want to announce is a scholarship. Our school gives an excellent scholarship. It's the Converse Scholarship. And yes, it is the same family who owns the tennis shoe Converse. And they've donated a lot of money in the past, given out some excellent, excellent scholarships. They're broad-based. They've got a whole slew of things from, and I want to double check this, but it says here chemistry, it says physics, it says, and it doesn't say engineering in general, but I think it is, and that's why I wanted to pass it out to you guys, because actually what it says here is computer science, computer network engineering, chemistry, electronics, math, physics, but I think it implies in there engineering in general, electrical engineering. No, it does not.
They don't even let you apply if you're listed as an engineering major. You're not even allowed to submit the application. You have to change it to one of those.
Okay.
That's what I was told.
Okay. Okay. Well, nonetheless, I'm going to pass this out, and I'm going to double check with that because they're a lot of money. They're $2,500. They've given out 20 of them in the past, and even with that said, do whatever you can to apply because they actually have less applicants than they have money to award. And that's happened in the past. And so I think part of it is what you said, that a lot of the engineering students don't because maybe they don't fit. Okay, so that's going to be a bummer. But certainly those of you who are in physics or mathematics or chemistry, I know you fit with this. And that's why I wanted to take the time to make sure I got this in the hands of everybody who at least would qualify, because I think it would be a shame if some good scholarship money that I know people could use sat there because people didn't know about it. And that's happened in the past. Because the other thing in our scholarship book, it's kind of listed on the side and it doesn't really stand out. It's kind of listed in a cross-discipline because it has so many disciplines listed that I know a lot of people didn't see it. So I'm suspecting that's what happened because it has happened in the past where the students apply for scholarships in the spring and they just didn't apply for that one because they didn't know it was there. They didn't make the connection. And so anyways, the closing date is the 27th, so that's Friday. And so the timing was perfect in the sense that you can still study for the test, you can take the test on Thursday, and then worry about this Thursday night and Friday.
When they do it through the school, through the foundation, I've already got it twice, and I've never not been an engineering major.
There you go. So, and you just checked engineering major, right? Yeah, yeah. So I know that's happened in the past, so I know you said that, but A, don't let that discourage you. B, I'll ask them more questions in particular, but, you know, it's a lot of money and it's a great gift and we're lucky to get it, and I know the people who have given it really want to see it go to people who need it and help them with their education, and they put the money in the STEM fields purposely because they want the money to go into the STEM fields. Yeah. All right, well, excuse me, those are the big announcements. Let's go to 13. I'll start with number 13 out of your book. I'll read it so you can all see it. We'll go through those same basic steps again. And if you recall where we left off on Thursday, is we had said that if you hook up a circuit with more than one capacitor, you can write the equivalent of that. And that's what this problem is really leading to. In fact, I'm going to tie it together with number 12 because as you will see, it starts off and says something about number 12. 13 is really a continuation of number 12. But I'll read number 13. It says, what if the two capacitors back in problem 12 are now connected in series? And in 12, they were connected in parallel. And so I think the parallel one's a little bit easier, so that's why I picked 13. But let's go back. Let's go back to step number 12 and try this. We've got two capacitors as it says in number 12, two capacitors, one of 5 microfarads and the other of 12 microfarads, are connected in parallel, and that resulting combination is then connected to a 9-volt battery. So here's what they mean by that. Looking then at number 12, they have two capacitors. I'll call it C1, which is 5 microfarad, and another capacitor, which I will call C2, which is 12 microfarad. Let me just confirm those numbers, 5 and 12. They say hook them in parallel. All right, well, let me pause right there. Because one of the things you're starting to learn in lab, and of course you're starting to learn into the lecture here, is what is parallel, what is series. And we use that name real quickly at the end here, but here's what we mean by parallel. That if you were to look at a plate on each of them, they're connected together. Remember, they're connected with a wire. Remember, we said conductors always have the same potential. And so whatever this potential is, it is the same on the top plate of each capacitor. Likewise, and I think it's nice to change color here, if I were looking at the other plate, which I will do it in green, that whole green line, being a conductor, all has the same potential. And so one of the challenges, as I said last time, and I hope we'll demonstrate here today, is as you go to figure out what the equivalent capacitance is, since we had different formulas, whether they were in series or in parallel, you have to recognize, are they in series or are they in parallel? And so one of the easiest ways I find to do it is to draw a color along a wire, because everywhere along that wire that is connected, being a conductor, must have the same potential. And so what we have is the blue to green, the same voltage difference. And that's what we said last time about things that are in parallel. We called them parallel because if you were hooking them up, maybe you better stick to that color again. And I was connecting them with a battery, then the electrons that come off of this battery here can move along, and as we said, the first one might go on capacitor number 1. But of course, once that starts to create an electric field, that's an opposition for more to come on, so they begin to go in other places. And in this case, it's 2 other places. But as the electrons begin to pile on, the electric field builds up inside of them. But it was this whole idea that we would have electrons on one side, which would chase electrons off, finishing the connection with our battery. But it's this electric field then that builds up, builds up, builds up. And we said, not forever. When does it stop? Yeah, when the voltage here is the same as the voltage here, which is the same as the voltage here. And in this problem, they say you're connecting it to a 9-volt battery. Okay? And all this is to say, when I read the problem here in step 12, where it says they are connected in parallel and they give me no picture, this is the picture I need to draw. 2 capacitors in parallel, meaning they have the same voltage, or maybe the result is that they have the same voltage. Okay? Well, again, continuing with number 12, it says here, what is the equivalent capacitance of this combination? Well, that's the easier the one. That's why I'm going on to 13. But we learned that the equivalent capacitance was the sum of the 2. And so we went through a little derivation at the end, although we haven't got a chance to do any examples. That's why we're doing it now, and we're saying then if you just add them, you get 17 microfarads. And so you could redraw this circuit if you wanted, and saying, all right, this would be the same as a 9-volt battery, then connected to a single 17 microfarad capacitor. And even though this is not the real circuit, there are parts of this equivalent circuit that become very useful to the real circuit. And that's why we learned about equivalence. And you're going to see that not only now, but next couple of chapters where we get into resistors. We'll go equivalent resistors. And that's why we'll look to see, are they in series? Are they in parallel? Let me throw something else out there. Are they neither? Because I think this early on in your education, students always think, oh, they're either in series or they're in parallel. There's also neither. And so don't miss that. And we'll emphasize that as we go later on. But for right now, everything we're going to draw is either series or parallel. Guarantee it. But there's also the neither. And so we've got to say, what are we going to do there? But not today and not before the test here. But I answered the first part. What is the equivalent capacitance of the combination? B, what is the potential difference across each capacitor? Well, you can see why 12 is the easy one. What is the equivalent, what is the voltage across each of them? Yeah, you already told me. It builds up to 9 volts. So maybe I'll just put 9 volts there, 9 volts there. The equivalent capacitance means that this equivalent capacitor would build up charge until it got to 9 volts. And then C just goes, what is the stored charge on each capacitor? This is where, again, the equivalent capacitance is nice, but really not needed here. Don't you already know the capacitance and voltage? Don't we have this relationship that capacitance is the amount of charge per volt? So as long as you know 2 of these 3, you can find the third. And again, that's why 12 is a little too easy as an example, but it leads into 13, and that's what I want you to see. And it leads into the harder one I really want you to see in just a moment here. But this first one, I would say C1 then is the charge on number 1 divided by the voltage on number 1. Meaning the charge on number 1 would be simply the capacitance on number 1, which is 5 microfarads, times the voltage, which is 9 volts. And of course, 5 times 9 is 45. A micro times anything is still a micro. I'll leave that alone. But maybe worth pointing to the units. What did we say was a farad again? Okay, yeah. Coulombs per volt. And so this volt would cancel with that volt, and you've got coulombs. So 45 microcoulombs is the answer to the first one. How much charge is on here? And then number 2 would be the same basic idea. It would be capacitance number 2 times voltage number 2. But again, given that they're in parallel, the voltage is pretty easy to get in this case. This is the 12 microfarads times the 9 volts. And same idea, 108? 18, yeah. Micro, and then that would be coulombs again. How much charge came out of the battery? Yeah, and so we would need to add these together. So 45 and 8 make 53. So 153 is what came out of the battery. And so it came out and split at this node, and some went this way, 45 went that way, and 108 went the other way. And hence the word parallel. They can come along, they can hit a node, and they can spread out. They can either go direction A or direction B. Yeah.
Why did so much more go to 2?
It's a larger capacitance. So remember that what is keeping the charge from, making, say, all of it go on one capacitor is the strength of this electric field. Okay? Now, the strength of that electric field has to do with the charge density. And so if this capacitor is physically a larger area, which is why it has more capacitance, you're going to have to put a lot more charge in order to get the same volt. So the analogy I had last time was this giant tank, and if we take a rubber hose here and we fill up a smaller tank and a bigger tank, what happens is they begin to fill up equally at the same level. Not the same amount of water, but the same potential, the same height. Right. And that's what's happening here. As these are filling up, they will go to 1 volt, 2 volts, 3 volts, 5 volts, 9 volts. They will go up in voltage together. That doesn't mean they have the same charge. And that's an important concept. What's the same, the potential or the charge? And in this case, it's the potential. It's a little different in the next one, though. Yeah.
That came capacitor and series, they have the same charge, right?
Yes.
Was that same charge still based off the first capacitor in the line?
Yes. Yes. Which is what I really wanted you to see in 13. So, like I said, this is number 12. This is, I think, a little bit easier to see, but it helps to see that one in contrast with number 13. Number 13 is what you're asking about in series. And so 13 says, what if these two capacitors that were in number 12 are now connected in series with the 9-volt battery? Well, let me start by drawing the picture. And so I would start off with drawing the battery. There's the 9-volt battery. And series means that the two capacitors are hooked a little bit differently. What it means is that the electrons come off and chase another electron off of the first capacitor, so something like this. They come off, and I have a capacitor, and so as the electron comes off and piles here and chases an electron off, where does it go? Well, it's got no other place to go but the next capacitor. Of course, it chases off an electron and finishes the circuit, or finishes the chemical reaction, the redox reaction that is happening inside of our battery. The second electron would look something like this, where again it would chase one off and it would go to here. And the whole point was, if we call this capacitor number 1 and capacitor number 2, how does the charge on number 1 compare to the charge on number 2? Which was really your question. What are they? They have to be the same. So Q1 is equal to Q2. And what I was trying to show at the end of Thursday, and I'm just going to overemphasize it again here today, it's because of the way they're hooked up. It's because of how the electrons can flow into different places. We end up with a different type of circuit, a different thing happening. And so series needs to be treated different than parallel. That's why we had a different set of equations. And we get different phenomenon because of it. And that's why you have to recognize then what is a series circuit and what is a parallel circuit. And for many of you, this is the first time you've seen series and parallels. Others of you, this is old hat. But for many of you, it's the important skill to learn before Thursday when you look at something and go, okay, is that in series or is that in parallel? So this is a parallel connection. This is a series where it goes from one into another. And series, as you pointed out, would mean the charges would be the same. And that's different than over here where the forces balanced. That means the voltages were the same. And so, as we will hopefully soon see, do these capacitors each charge up to 9 volts? No. Again, what's different here is the electric field begins to develop inside the capacitor. And as another electron tries to get over here, it is being opposed or pushed back by this one and this one. These are working together to push them. And so what we said is the voltage number 1 and the voltage number 2 adds up to the total voltage of the battery. And that was a big difference. Over here, we had voltage 1 equals voltage 2, and the charge number 1 and the charge number 2 added to the total charge coming out of the battery. Those roles were exactly switched when we came over here to parallel. And that's how we derived the equations, if you recall, for calculating equivalent capacitance. We use this. For calculating equivalent capacitance in series, we used this. And you might recall then we got the harmonic sum, not the sum. And so this is our equivalent capacitance for something like that. And as you'll see, the voltages of each of these then are less than 9. The total adds up to 9. It's a very different scenario. And that's what this example is really trying to illustrate, because it says here, find the equivalent capacitance of this combination. And so I would like to know what is the equivalence. And then obviously, I'll put the numbers the same. Let's see, number 1 we called a 5, and number 2 we called a 12. And so let me write this as 1 over 5 microfarads added to 1 over 12 microfarads. Then take the reciprocal of that. And so I'm going to write it this way. I'm going to leave that alone and then just put a giant reciprocal on there. The reason for that is I'm going to encourage you that I think it's easiest to do this on your calculator with your reciprocal key. And so find your reciprocal key, the 83. It's just kind of over here on the side. I like it. It's easy accessible on the 83. But it makes these calculators pretty straightforward. Because if you hit 5 reciprocal key plus 12 reciprocal key, enter, reciprocal, enter, you're there. Okay, and it's just a couple of steps using the reciprocal key. And so what you'll get, in this case, is 3.5, I'll go 3.53 microfarads. And so easy access to that reciprocal key is very nice. It's short, useful, but with all that said, do whatever works for you. If you like to go 1 divided by 5 plus 1 divided by 12, and then some more, feel free. But it's nice that the reciprocal key is there. But that's A. What's the equivalent capacitance of these two? B is then, what is the potential difference across them? Here is really the first illustration today of why equivalent circuits can be really nice. What you have just done in A is to say that this circuit is the equivalent of that circuit. I mean, the real circuit has 2 capacitors on it, but the equivalent one would look like this. What's nice about that is if I go to calculate the charge on this one, it's real easy, right? It is just the capacitance times the voltage. The capacitance I just did, 3.53 microfarads. And this one's really easy to see that it would charge up to 9 volts. Fair enough? Whereas when they're in series this way, I'm not sure what the voltage is on here. I just know that the sum of the two come out to be 9. And so if I look at this equivalent one for just a second, it can be helpful in realizing that about a 31.8 microcoulombs flow out of this battery and onto this equivalent capacitance. Now again, this is an equivalent one. So the only usefulness of this is, does it help me with this? And I say it does. What does that tell me about the charge right there? Yeah, 31.8 microfarads. Because this one, which is, like I said, fairly easy to figure out what the charge is that comes out of the battery, when I take it back and I look at the real circuit, I see that same amount of charge that comes out of the battery must end up on capacitor number 1. And so I know how much charge is on capacitor of number 1. And like I said, that's a good usefulness of why we do these equivalents. Oh yeah, a bunch of questions.
You can control the number of charges by the capacitance?
Yeah.
Depending on what capacitance you put?
Yeah, if I had a lower capacitance here, obviously for that 9 volts, I'd get less charge.
Is that helpful for like safety issues or something, if you're trying to make something safe?
Exactly. Exactly. You may want to know, you may want to have a lot of charge, or you may want to have a little bit of charge. Right now, and before today's over, maybe I'm glad you remind me. I'll give you another good application of capacitors. But what you saw so far was me just taking a capacitor and trying to put a lot of charge on there so I can run a light bulb for a long time. So in that sense, I would want a lot of capacitance to get a lot of charge. But there's other reasons I'd want very little charge. Oh, I guess I did talk about that coaxial cable and how it slowed down my internet connection. So in that case, I would want a little bit of capacitance. But there's something else to see. But I'll wait until we get to a problem and point out on the diagram. Okay. All right. Now, as I said, keep in mind that equivalent circuits are nice, but they're not the real thing, right? They're only nice in the sense that how does it help me with the real circuit? And so I'm going to come back over here and say it has helped me with the real circuit. It has told me the charge on capacitor number 1. And hasn't it also told me the charge on capacitor number 2? Because we just argued that they would have, whoops, microcoulombs. Microcoulombs. We just argued that they would have the same amount of charge when they're in series. So that was the neat thing about that equivalent circuitry. And it finally gets me to the point I want, which is what is the voltage on each of them separately? Yeah.
Is it safe to say that there's a voltage drop across each of the capacitors in series?
Yeah. So there is a voltage change, drop, difference. What word do you want there? There is a change in voltage. Yeah. And that was the question, I believe. Now I've kind of forgotten what I was after here. But the potential difference across each capacitor, the voltage drop. And really the only thing I know is that the two of them together must add up to 9. But here was nice about doing the equivalent. I got the charge. I got the charge on each one. And once I get the charge on each one, then I can actually get the voltage, because the voltage then would be the charge divided by the capacitance. And so this would be 31.8 microcoulombs divided by 5 microfarads.
That's for the total.
No.
Oh, that's the first one.
This, is just number 1 here. So if I go 31.8 and divide it by 5, I get 6.36. And I guess I should check my units, especially since these are new units to many of you. A micro would cancel with micro. That's good. Remember what a farad is. It is a coulomb per volt. So coulombs would cancel off, and I'd be left with volts. Okay. Is it warm? Can I open this? Crack it a little bit? Or think you're cold? I'll do that much. How's that? All right. See if that helps. And so there would be the voltage on the first one, which is excellent because now I can either do the same thing to get the voltage on the other one or know that the total adds up to 9. But this will also give me a chance to confirm it. So I'm going to do the same calculation here and go 31.8 microcoulombs of charge are also on number 2. And 31.8 divided by 12 gives me my 2.65 volts here. And then hopefully, when I add those together, I get 9, other than it rounds up to 9.01. So, other than a little bit of rounding there, I have got the voltage. And it confirms that. One thing I think you will find with the circuitry that you'll see this chapter for the first time and the next couple of chapters is by the time you get done, you'll see that they've got to be self-consistent with other approaches. So you really could know right away, did you do it right or did you not? Because if you do it this way to get the voltages, they should have added up to 9. If you did this one first and then added it up to 9, then you can go over here and confirm to see if it matches. And so it's really nice on a test to know that you can walk out going, okay, I put the voltages and charges in those boxes and they all matched up, and good. Because if you did a mistake, you would have caught it right there before you left. Well, I think there was a part C on here. Oh, I did it in the process. The charge on each capacitor. So it asks for the voltage and the charge for each. What I would like to do then is use these first two as setting the stage for really showing you a bunch of capacitors, not just 2 capacitors. What if I had a circuit that look like this. And so I'm just going to make one up. There's some pretty good ones there in the book. But what if I just take that same 9-volt battery and I hook it, say, to capacitor number 1, which is then maybe connected to capacitor number 2, which is then maybe connected to capacitor number 3, which is then connected... I'll do a fourth one. I'm just deciding, should I put it here? Whatever. I'll put it here. Hopefully, of course, you'll see the bigger principle that it wouldn't matter where I put it, right? Top of your syllabus, top of your test. A few fundamental ideas explain a universe of phenomena, right? And so I could put 3, 4, 5, an infinite number, right? I can put them in series, I can put them in parallel, right? And we should be able to work through this, taking these steps together. So let's use this circuit. Here's a circuit that has 4 capacitors in it. If I make a little chart here that says, okay, C 4 capacitors, I'll put number 1, number 2, number 3, number 4. We could give them some value, 10 microfarad, 20 microfarad, 30 microfarad, 40 microfarad. Hopefully the exact value doesn't really matter, right? So how they're hooked, what their value, it's the procedure, right? The logic is still going to be the same. And then we could simply ask, what is the voltage on each capacitor? What is the charge on each capacitor? And I'll take this one step further. What is the energy on each capacitor, right? And so here I have a bunch of capacitors hooked up. All right, well, this one hopefully will really illustrate equivalent circuitry here and the advantage of it. And please remember, the equivalent circuit can be useful, but only in the sense, how does it help you with the actual original circuit? So look at this for a moment. Do you see anything that might be equivalent? Do you see anything that I can kind of put 2, 3, or 4 capacitors together? Right. And I'm glad you guys see 2 and 3 are parallel. Sometimes it's hard to notice. I'll try it again, right? I'll take maybe my red pen. I'll kind of draw a red line around this wire. What do I know about that wire? And everything touching that wire, it all has the same voltage. If I take another color here in green and I say, all right, if I draw green, 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 I can see that these two go red to green, right? They have the same voltage across them. I don't have that for C4, so C4 must not be parallel with those two. C1 must not be parallel with those two. And so what I have really as I look at this is just C2 and C3. They're in parallel. They're not in series, right? To be series, I would be drawing a line from one plate to the other, and that's it. And that's not what happens. I don't go from one plate to another. I don't go from one plate to another, and that's it. I go from one plate, oh, split, bummer. From here, split, oh, bummer. Right? So this is not series, this is not series, but this is parallel. And so my first step might be to redraw this and say this is equivalent to C1 left alone, some other value, C4 left alone, like that. So that's what that is equivalent to. And I could even calculate it, but I'm going to hold off on calculating it because when I draw that equivalent one, hopefully some other things go on in your mind. What does that look like? Right, and so if I were drawing some lines here, I could say that all of the electrons that come off of this plate have no place else to go but to that plate. And that's what we meant by series. So C4 and this equivalent one. Maybe I'll label it as the equivalent of 2 and 3. But that 4 and that equivalent are in series. In fact, do you one better? What about this equivalent and C1? Yeah, and so all three of these are in series. And so I'm claiming that the equivalent of that circuit, which was already the equivalent of that circuit, would be something that looked like this. And that's the one I'll just say equivalent, meaning the total equivalency of all four capacitors. And so I know the real circuit actually looks like this. The real circuit has four capacitors in it, but if this or this is anyway useful to solving this question about what is the voltage and the charge and the energy, use it. And that's the whole point here of our equivalent circuits. And so it is. Let's start here. This one, if we do some numbers, the 1 and the 4 are going to remain unchanged, but what is the equivalent of the 2 and the 3? Yeah, they're in parallel. So you would add them together. And so the 20 microfarads and the 30 microfarads become 50 microfarads. And so that's the equivalent of it. Here's a fun one to do. What's the equivalent of this one? Okay, so it's a harmonic sum here, right? And so it's got 3 terms instead of just 2. And I only did 2 for you in class to show you, but I'm hoping you saw that the way it was done, where the voltage had to add up to 9, when I had 2, what do the 3 voltages here have to add up to be? 9, right? And so if we were to work with 3 in series, you would have something like this, which comes out to being 3 terms being the equivalent. So C1, C2, and C3. So not obviously a complete proof, but an extension of the one we did for 2, if we did it with 3, if we did it with 4, if we did it with 5. And so the general idea here is if they're in parallel, the equivalent is just the sum of all the individual ones. Because you could have 3 or 4 or 5 in parallel. If they're in series, then the equivalent is the harmonic sum of 2, 3, 4, 5, 6, 7. And then it makes that reciprocal key a nice button again, because I can put into my calculator fairly quickly the reciprocals of each one, and then just take the reciprocal of all of that. And so the first one is a 10, so I'm going to go 10 reciprocal key. Add to the 50, hit reciprocal key. Add to the 40, hit reciprocal key, hit enter, reciprocal, enter. And I heard somebody say it already. Just make sure I got the same number. So I go through all this. I got 6.90 microfarads. So that's what you got? Yeah. Okay. So that's the equivalent. And again, just to emphasize, these circuits, of course, aren't the real circuit. This is. But those can help me get the answer to the real circuit fairly quickly. All right, here's why. Let's look at this overall equivalent circuit. If you were looking at just this circuit and this was 9 volts and the equivalent capacitance is 6.9, couldn't you tell me right away how much charge goes on to that one? Right? Isn't capacitance just charge per volt? So the charge is capacitance times the voltage. So looking at this circuit, which again, it's the equivalent circuit, it's not the real thing, but here's where it's useful. If I look at that and I put 6.90 microfarads for the equivalent capacitance, and I multiply it by the 9 volts, see, that's the real nice thing about it coming all the way down to one capacitor. You know that the one capacitor is going to build up a charge to 9 volts. Whereas these guys, you don't know what the individual voltages are. Although you do know that those two have the same voltage. That was nice, but we don't know what that is. Now, we do know this. that if you think about the voltage from C4, then the voltage from C2, then the voltage from C1, you got to get to 9 volts. There's our conservation of energy. That the electrons are being pushed this way with 9, they keep building up in charge till push, push, and push is 9. Now, I like the analogy of gravitational potential energy. If this is where you park your car to go on a little loop hike, if you go this way and go up 9 volts or 9 meters, guess how many meters you have to come down to get back to your car? Exactly, 9 meters. So you go up 9 meters, you got to come down 9 meters. So I know that the sum of these three better add up to 9. And I know these two better be equal, but I don't know what they are individually. And that's where this can be quite helpful, because this does tell me the total charge on that equivalent one. 6.9 times 9 is 62.1. So 62.1. I'll leave the micro alone. Remember, the farad cancels off with the voltage part cancels off, and we got 62.1 microcoulombs. And so what you're really saying is if you had a circuit like this, 62.1 microcoulombs would go on here. Well, how is that useful? Is that really important back here? Well, absolutely. Look, comes out here. Where does it go? Only to capacitor number 4. So this must be 62.1. That's why it's really useful. I can answer the question, how much goes on capacitor number 4 right there? Of course, as you watch it then, the 62.1 come off and split. So some go here and some go there. So I don't know what the charge is on these guys, but what I do know is that they add up to 62.1. Because that's going to help me here. How much charge gets onto C1? Yeah, 62.1. And so I can fill in at least 2 of those boxes knowing how much charge is on 1 and 4. Now, watch this. Here's the other nice thing about equivalent. I haven't looked at this one yet, but this can be very helpful at this point. If you compare this to this, knowing that we just calculated 62.1 comes out of the battery and goes here, that means 62.1 goes on to capacitor number 4. So how much goes on the equivalent of these two? Yeah, this is 62.1 on that equivalent, right? So could you get the voltage on that equivalent one? Yeah, it's Q over C, right? And so your Q is the 62.1. Your capacitance of this equivalent is 50. Let me just double check. These are each micro. So 62.1 divided by 50 is 1.24. And volts, since this would be coulombs and this would be farads. So right here, this equivalent one has a voltage of 1.24. Now again, that's an equivalent circuit. So the only reason I would care about that is, can that help me over here at all? And yeah, these two are in parallel. They have a voltage the same as this guy, right? Because all you've done is replace those two with this one. And so now that I have found the voltage on this equivalent one, I can come over here and say that is the voltage on each of those. Yeah.
But since they don't have the same capacitance, they don't have the same charge.
Oh, right, right. I'm not saying they have the same charge. Now, they must add up to 62.1. And we'll confirm that in just a second, but keep this in mind, that the capacitance is charge per volt. So if you know any two of these three, don't you also then know the third? And that's what I have here, right? I've got two, I can get the third. 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 And so I'm ready to wrap that up. And then the energy is just those guys put together. I'm done. Right? And so the equivalent capacitance made it really easy to figure out what the total, what the charge is on two of them. And that made it really easy to find the voltage on the other two. And then I'm really done here. Because voltage would be the charge divided by the capacitance. That's just divided by 10. So that should be 6.2. The charge should be those two multiplied together. 20 times 1.24. Well, it should just be 24.8. These guys, 30 times 1.24 should just be a 37.2. And then the voltage should be the charge, the 62.1, divided by the capacitance of 40, coming up with 1.55. Okay. And so now I've answered, at least most of it. I still have to do the energy, but I'm waiting on that one. But that's really what I wanted you to see. That what we can do is take a bunch of capacitors, whether it be 2 or 3 or 4 or 5 or 6, we can put them together, we can get the equivalent. Each of those equivalents will make it pretty easy, depending on which circuit you look at, to figure out the charge on the voltages on the other one. And we should probably check these out to see if they make our confirmation, to see if we made any mistakes along the way. Because you guys already told me that these two got their charge by what came off of C4. So these should add up to C4. Do they? 10, carry 1, 11, 12, carry 1. Well, other than a rounding in the 10th, it works, right? Good. Also, I mentioned, and I guess I should say, I would call that conservation of charge. The other important thing was our conservation of energy. And what I was saying is these will build up charge until the push backwards is 9 volts, because that's what this is pushing. Or as I like to say, if this is a trailhead, you park your car right here. If you go around a loop, you better go uphill as much as you go downhill. You add up all those voltages, the change in voltage better come out to be 0. Conservation of energy. Otherwise you would end up with more energy than you started with. Okay? And so let's give it a try. If I go this way, I would increase by 9 volts. If I continue on, I would go down, down, down. So notice I am not saying that all 4 of these should add up to 9. Very common mistake. I'm not saying that at all. What I am saying is this trail, 1, 2, and 4 better add up to 9. 1, 2, and 4. Do they? 8, 9, carry 1, 10. Good. Comes up to 9. So they do. And likewise, if I were to go up to here and over here, they better add up to 9. So 1, 3, and 4 better give me 9. 1, 3, and 4, add them together, and you get 9. Right? So it does work. Which that's not any different, because these were the same numbers. So if the other one added up to 9, that one has got to add up to 9 too. But we can confirm all that. The other part we did all this is we said we could get the energy from each individual one. Well, this is the easy part once you get this far, because we learned that the energy is 1/2 CV squared. So you already got all this stuff. Well, I can get the energy now. I can go 1/2 times C, which is 10 micro, times the voltage, which is 6.21, and square it. Then I come up with 192.8. I suppose I should keep track of my units here. There is microfarads. These are voltage squared. I'll leave the micro alone. But a farad, if you remember here, is our coulomb per volt. So one of the voltages go away. And our, coulomb I'll leave alone, but our voltage was a joule per coulomb. And so we get left with joules. So that capacitor is 192.8 microjoules of energy stored on it. And we could go all the way through here and do exactly the same thing for the other ones. 1/2 times a 20 times a 1.24 squared comes out to be a 15.4. 1/2 times 30 times 1.24 squared comes out to be a 23.1. And 1/2 times 40 times 1.55 squared comes out to be a 48.1. And so each of them have a certain amount of charge, a certain amount of voltage. The total energy then would be stored on, the total energy is what is stored on all of these, yeah.
Isn't potential also charge times potential? I mean, potential energy isn't also charge times potential?
No. It's charge times potential added up. So if I was building the energy on a capacitor, at some point there would be a voltage difference, and I would move a charge dq from one to another. So the change in energy as I move it across would be the amount of charge times the voltage, right?
Can't you use that for that one?
No. If I add these up, I do not get V times Q. Why not? What have I done wrong in that integral?
V is not.
I have just treated V as a constant number, and as you are moving charges, the voltage starts off small and gets bigger and bigger. So no, don't do that. Okay? You can replace that dq here with our voltage, which we said was the charge per capacitance. And that's how we came up with the 1/2 total charge when we add up from 0 to capital Q over C, which is our 1/2 CV squared, yes. So that's where the 1/2 came from, is we were adding up our voltage step by step by step. It's not the total voltage times the total charge. If you did total voltage times total charge, you're going to get a number too big, because the first charges don't work out that way. Now, just out of curiosity, how much energy is on this equivalent one? Well, 1/2 times C, which is 6.9, times the voltage, 9 squared, equals 279.5 microjoules of energy. And I bet if I add these together, I will get the total energy stored in this circuit. So 192.8, 15.4, 23.1, 48.1, coming out to be 279.4. So again, other than that little bit of rounding along the way, I'm not surprised. And in fact, if the question had just asked what is the total energy stored in the circuit and not what is on each capacitor, I would have just done it right here. I never bothered to find out what the energy is individually on them. And so hopefully everything kind of checks out. And that's the big grand finale, if you will, of that one. I wanted you to kind of run through all that. Let's look at some other circuits here. Those kind of all fit the same idea. But I think it's number 19. Yeah. The author gives you a nice little circuit there But again, one of the challenging parts of these problems will be really kind of understanding the physics of what's going on so that you can go, well, what is the same? For example, when they were parallel, we looked at it and we realized from the physics of it that the voltages had to be the same, not the charges. When they were in series, we looked at the physics of it and said, well, the charges have to be the same, not the voltages. Well, this is a good problem for exactly that same reason. Is here's something we haven't explicitly done quite yet, but if you understand the basic physics of it, this is going to be simple. If you don't, you're going to miss what remains the same and have troubles answering it. So here's our circuit. Now, another reason I wanted to grab this one is they've thrown in S's. What the heck are these? Yeah, the S stands for switches, so I brought a couple of switches to kind of illustrate here. Here is literally what a switch looks like when you are turning on and off the lights. And in this case, I think the diagram does a good job here. Here is the switch. When you close it, you now have a connection, a metal connection. Charges can move. When it is open, they can't move. So in this case, we have two. Okay? Kind of a simple switch. I'll point out, because we'll see other switches as we go along, these are what we call a single pole, single throw. Because if I contrast that with this one, this is a single pole, but it can throw in two ways. So it's a single pole, double throw. And we'll see some of those, not this semester, I mean not this chapter after the test, but I can make a connection to one side, or I can make a connection to the other side. Or, yet the more interesting and complicated ones, if you can see, on this side, I have a pole that can be thrown that way and make a connection, or it can be thrown that way and make a connection. And the same thing happens on the other side. So it is a double pole, double throw. And I can be making connections two at a time to something connected or totally different depending on what I'm trying to hook up. Well, we'll keep it simple here, right? Single pole, single throw. There's my switches. So the other ones you know about, here's capacitors, here's voltage. Let's read the problem here. Here's what it says. It says, consider the circuit shown in figure 19. C1 is 6 microfarads and C2 is 3 microfarads, and the delta V is 20 volts. Capacitor C1 is first charged by closing switch S1. Okay, so if you kind of look at what we have so far, what do you think would happen if you closed only switch number 1? So you take the first switch and you close it. Yeah, see, you have made a contact with capacitor number 1, but not capacitor number 2. Okay? And so it would be like you're thinking, okay, this doesn't exist, right? All right. And so that's what they do first. Switch S1 is then opened. And the charged capacitor is now connected to the uncharged capacitor number 2 by closing switch 2. Now, did you catch the order here, right? So we first did this. We first closed switch number 1, and then, before we close switch number 2, we open. Now let's pause right there. What's that going to do? Okay, so what we have then is a capacitor that now has energy, right? It now has charges on it. It has voltages. And when you disconnect it, it can't get more energy from the battery. Or for that matter, it couldn't send energy back into the battery. No charges can go that way. That's the key to the problem. Because then, what happens when you close switch number 2? What will happen? Anything? Will charges move? Yeah, charges will move from C1 to C2. Will all of the charges from C1 go to C2? No? Half of them? So what will be the same here? They're in parallel, they'll voltage. You see what's going to happen is this electric field is pretty strong in here, and at first it's a lot stronger than this one. So as charges come dumping off of here and going on to here, this voltage is going to go down, down, down. It's losing charges. This voltage is going to go up, up, up. They will eventually balance when their voltages are the same, right? They're in parallel. And that voltage will be 10 volts?
Half of the battery.
Half of the battery?
Some of them will be equal to the original
Do I know it's going to be half as much? No, I'm glad many of you are struggling with that. We don't know it's going to be half as much.
That should be, huh?
And it won't come out to be half.
No?
There's no reason that it should be half. So tempting to say it's half. Just so want to so badly. It's not.
But if they're the same.
If what's the same?
The same capacitors.
Well, they're not. Right? Okay, if they were, it's a different story. All right, fair enough. So, okay, in the special case, I'll go with that. But that's not the case we have here. So how are we going to handle this?
If you're connecting only the two capacitors and you fill up the first one, it's kicking off the electrons from C1 that's going to the battery when the first one is closed. With the second one, when the first one is open, the second one is closed, there's nothing really being moved.
And so what are you saying by all that?
That no charge is going to go to C2.
No charge will go to C2? Oh, no. A lot of charge will go to C2. Definitely there. So if I kind of draw a little diagram of what's happening, here's what would happen first, right? We do have 20 volts. We're told that. We close switch 1. So it's like the other capacitors, not even there. So let's just talk about that. That's the easiest one. I think you could do hands down, no questions about. You could just figure out what is the voltage then on number 1 at this point? 20 volts. What's the charge on number 1 at this point? Okay, so it would be capacitance times voltage. And the capacitance, I forgot what they said here. Number 1 is 6 microfarads. So it's 6 microfarads times 20 volts. 6 times 2 is a 12 with an extra 0 microcoulombs. All right. So this much you guys didn't seem to have any questions about at all. Just look, that it's going to charge up. It's not going to charge the other capacitor. The other capacitor is sitting over here kind of by itself. I think it had 3 microfarads, which was what we're going to need to talk about in a second, yeah. And it's just kind of sitting over there, kind of hoping to get its fair share of charge here. Not there yet. But a real key important point was the next step, where this 120 being on here means that there's an electric field. And these charges would like nothing better than to race around and go back over to there, which you saw me do when I short-circuited that capacitor and saw the spark so you could see the energy did. But as these charges try to leave here, they can't go anywhere but accumulate on number 2. So yes, charge will build up on number 2. And as it is building up, the voltage here, V1, will go down. So it will be less than 20. The voltage here, number 2, will go up. It'll be greater than 0. This will stop moving once V1 equals V2. But that doesn't necessarily mean they're 10. So how am I going to approach this?
How much charge
capacitor.
Conservation of charge, right? I know that back here in this beginning part, I put 120 microcoulombs on there. And so as some charge comes off, I am left with only a little bit of charge on C1, or a lot, I'm not sure. But where did it go? And that is to number 2. And what I do know from my physics here is that the total amount's got to be 120. That's the real key to the problem. Those two have to add up to 120. And I claim then if you put that idea with that idea, you'll have 2 equations, 2 unknowns, and you can solve. You can solve for the charge, you can solve for the voltage. Let's give it a shot here. How do you get the voltage again? Well, yeah, Q over C. Q over C. Right? And so charge number 1, well, we'll just wondering if I did it this way, I wouldn't have to deal with fractions, but I'll deal with fraction. But this is charge number 1 divided by capacitance number 1, which, what did we say that was again? 6 microfarads. And this one, charge number 2, then over 3 microfarads. If I maybe bring that over to here, charge number 1 then becomes twice of charge number 2. And so that's the ratio of the charges. They don't spread out evenly. I don't expect them to spread out evenly. I expect them to spread out with equal voltages. And equal voltages means I've got a 2-to-1 ratio. And if I now take that and put it into here, I can get charge number 2, or twice charge number 2, and then charge number 2 is 120 microcoulombs. So 3 times the charge on number 2 is 120 microcoulombs. So the charge on number 2 is going to come out to be 40 microcoulombs. Which means then back here, the charge on number 1 is 80 microcoulombs. And so they have a 2-to-1 ratio, and the sum goes to 120. Which I think was the question. Was it the energy or the voltage? But let's do all of them above. It says calculate the initial charge on C1, which I did, and the final charge on each of the capacitors. So I've answered their question, but let's just see what the voltage then comes out to be. The voltage should be charge 1, which is 80 microcoulombs, divided by the capacitance of number 1, which was our 6 microfarads. Of course, that should be the same as the 40 microcoulombs over the 3, which it is. And so the micros cancel off, and we get voltage. 3 goes into 30, what, 10, 13 and a third times? So my voltage is 13.3 volts. And so there would be the voltage. Not half, it's not the 10. Yeah?
If you then closed S2 or opened S2 again, it would change to act as if it was just one capacitor in the circuit?
Oh, well, okay. But remember, S1's already open. So what are you saying? You're saying open S2.
And close S1.
And then close S1. Sure. Now what would happen? Right. This has more potential, 20 volts, than this one, which we now said was 13.3. So what would happen is charge would now come off of here, flow. Oh, wait, which one's open? Okay, open. So it would fill that one back up to its 20 volts, with its 120 microcoulombs. And then C2 would keep its charge. At least in a perfect world, and you saw in the lab how those capacitors, they can stay there for a while. Some of you played with them, but you come back an hour later and they don't have that charge anymore. But
what if you do that over and over again? Does the C2 eventually get?
Yeah, if you kept doing this, obviously you keep dumping more and more charge on here because this is at 20 every time, and this is always a hair under 20. Eventually you'll bring that one up to 20 if you just did it a bunch of times. But if you just wanted to get them both charged to 20, why don't you just close both of them? And charge will come off the battery till both of them build up to 20. But, well. Ah, good. You guys are getting the right idea. All right, let's try this one. How about number 28? Yeah.
Physically, though, why don't they both have 10 volts? Like, what? Why would they split the voltage?
Let's see, how do I answer that? I have a tough time answering why it's not versus why it is. I mean, the physics behind it is charges are going to be pushed around until they reach equilibrium, when their net force is 0. So if I have an object right here, and it's being pushed left or right, going back to mechanics, if one force is greater than the other, it will move in that direction. Charges will keep moving then until a balance is reached.
Well, actually, I think the voltage is not linear. It's actually
Yeah, actually, you're asking a good question about the energy. Maybe before I erase this, we should just look at the energy here for a second. And I will in just a moment. But to kind of answer your question, I don't know if this helps a little bit better, but going back here, when I close this switch, you see what I have is a voltage created by an electric field. That's a push. I have a voltage created by an electric field. And if these electrons are being pushed by an electric field that is stronger than that, or giving it more energy, it will push. Again, if my analogy helps at all, if I have a tank of water and another tank of water, and they are connected with a rubber hose, if I start with one tank that is full, what will happen is water will flow, filling up one tank, diminishing the other tank. They don't go halfway because the amount of water stays the same. The amount of water is conserved, just like the amount of charge is conserved. So in this case, they would keep going until the pressures are equal, the forces are equal, the energies are equal. That's what they're after. Now, maybe by an extension of that will help you is, let's look at the energy here. You might be surprised here at the energy too. Back here on this one, when I first charge this one up, 1/2 CV squared, how much energy is that? Well, 1/2 times the 6 times the 20 squared comes out to be 1,200 microjoules of energy. That's how much is on that first capacitor. When I then close the switch and let it move from here over to there, I got a voltage of 13.3. So when I look at the energy that is on number 1, it's 1/2 times 6 times 13.3 squared. So this is 531 microjoules of energy. The energy on number 2 would be a 1/2 times a 3, which is half of the 6, times the same voltage squared. So as a quick calculation, I'm just going to divide by 2. But this should be 265 microjoules. Notice that when I add those two together, I don't get that. So again, I am not trying to say here that the energy before I opened the second switch and after is the same, at least the same as the electrical energy. I do still have conservation of energy. Where'd that energy go then? Yeah, and it kind of depends what actually happened here. Maybe to keep it simple here or not. When I make this closed right here, there's going to be like a little spark. A little bit of heat generated there when I kind of close that. You might even hear the spark and see it. So there'd be energy in light, there'd be energy in the sound, there'd be energy in the heat. So it doesn't surprise me at all that these two add up to something less than that. They do not add to the same one. Don't try to do this by conservation of energy. It will not work. Unless you, of course, know how much energy you lost in this connection. Because remember, conservation of energy only works if you add up all the energies, not just the electrical energies.
But shouldn't that, like the energy stored in C1 after closing S1, shouldn't that equal the total energy between C1 and C2 after opening C1 and closing C2?
No, because it can go other places. It can go to heat. It can go to sound. It can go to light.
Wouldn't that be like a fraction of the energy? Because it's just a small connection?
No. Well, I don't know. Do you call that a fraction? I mean, what does this add up? I mean, this adds up to almost 900.
So you have 300 lost.
We've lost 25% of our energy. I would not call that small.
In the same exact situation we just had, is C1 and C2, do they stay charged, or does some of the charge go back to the battery?
Oh, the way we did it, none goes back to the battery.
No, so they do stay exactly like that, kind of like your second picture.
Oh, yeah, and
You can move back
right.
into the battery after S1.
Right, once this is open, in a perfect world.
There's nothing pushing it back over.
But remember, there's going to be water floating around here. The water is going to pick up a charge, move it over, carry it with it. You're going to have a small conduction. A couple hours later, you're not going to have any charge left on that capacitor.
What part of these equations account for spark and light?
Well, nothing in my equations account for the spark or light. That's why I would not want to use conservation. If I did, I should probably write it this way. The energy I start with, 1,200 joules of energy, should equal the 531 plus the 265 plus the energy due to heat plus the energy due to light plus the energy due to sound. And that's why these add up to making it such that those don't add up to that. And so be careful doing conservation of energy. Conservation of energy certainly works, but you have to include all your forms of energy. And in this case, we don't have enough information to do all of our forms of energy. So this problem should not be approached with conservation of energy. There's just too many unknown other pieces of energy in there. Oh, good. That was a discussion getter. I like it. All right. Let's try number... let's see, how are we doing on time? I think you got that pretty good idea. And how are we doing on time? I'm going to jump to number 30. 30 is kind of a fun calculation to do. But it also illustrates some of our basic physics. It's one of these things, ideas, again, that, okay, I've never seen it before, but if I understand the physics of it, I should be able to reason out and do something that I've never done before, because it's based on the fundamental idea of the physics. 20, what number did I say? 30? Number 30 has a picture with it, so let me call up the picture. It's kind of nice to look at this picture here. Here's the circuit. It's got a battery, a switch, and a capacitor. Ooh, and two springs. I haven't done anything like that before. But you have, right? You've done Physics 121. You've done plenty of mechanics. You've done your circuitry. Put them together here, right? Let's read this one. Here's what it says. Number 30 says, the circuit shown in figure 30 consists of two identical parallel plates connected by identical metal springs to a 100-volt battery. When the switch is opened, the plates are uncharged and they are separated by a distance d of 8 millimeters. That gives it a capacitance of 2 microfarads. When the switch is then closed, the distance between the two plates is reduced by a factor of 0.5. A. How much charge collects on each plate? I'll just stop there. How much charge is on each plate? Now, I'll put some numbers in here. They've got our battery. Which way did they make it positive? Over here. Okay, so I've got a positive here and a negative here. This, they said, was a 100-volt battery. They've got a switch, which I'll draw it in the open position like they have it. Comes along, and there's a spring and a parallel plate, and another little plate and a spring, something like this. They say that before closing the switch, there is 8 millimeters, is that what I read? Separation? No, 30, 8 millimeters of separation. They say that that's enough separation to give you a capacitance of 2, I think it said, was it nanofarads? Oh, now I need to look. Or was it micro? 2 microfarads. 2 microfarads. Okay? But they did say something very important here. You close the switch, and the separation of those plates was cut in half. Why? Okay, right. So we're back to our physics here. Well, of course, what's going to happen is negative is going to build up on this side, positives are going to build up on this side, which is why we have an electric field, which is why we have voltage. But one thing we really haven't addressed is, wouldn't that be a pull or a tug there? Right? And so we'll pull them a little bit closer together. Now, they wouldn't go all the way close together because the springs are going to stop that. But they do say that this now is reduced to half as much, so we'll do 4 millimeters. Our first question then is, what is the charge on those plates? Well, that seems simple enough. Capacitance is charge per volt. It's not nearly as hard as those other ones. We've only got one battery and one capacitor, right? So isn't the charge just capacitance times volt? We know the volts is 100. That's pretty easy. We know the capacitance they gave us, right? It changed, right? Is it still 2? Yeah, that's the piece to grab. It's not going to be a 2 anymore. The capacitance has changed. Yeah.
Wouldn't we have a pull or a repulsion between the loops of the, because they say it's a metal spring.
Yeah.
So as electrons are going along the wire, we'll have like a repulsion between the electrons.
I suppose there's a little bit of negative that's on the spring, and you're saying the spring's going to help push it apart.
Closer together because of the springs.
Okay, but the real buildup of charge is when they're in here. So no, they're not after that. But I don't disagree. You're right. There's going to be some buildup of charge, and they're going to have an extra push from the spring. But that's really not going to change the dynamics of the spring. That force is really, really small for a lot of reasons compared to just the metal structure of it. But what I want to emphasize here is something that's really easy to overlook. This is not going to stay at 2. In fact, what is it going to become? It's going to become 4 microfarads. How do I know it doubled its capacitance? Yeah, the capacitance of a parallel plate capacitor, as we've been working with, has to do with the material inside, the dielectric constant. It has to do with the area of the plates, and it has to do with the separation. And so it's inversely proportional to the separation. So you cut D in half, which means the capacitance is going to go up by a factor of 2. So our capacitance, which was at 2, is now at 4. 4 times 100 is 400 microcoulombs. And so that's our charge on each of them. Capacitance does change. And then other than that, it's pretty easy to do the problem. That's really was the whole point of this step, and this particular problem was to get you to realize, wait a minute, if things move, the capacitance can change, which means the amount of charge. Because if it had not moved, if this had not moved forward or back, wouldn't the charge have only been 200? And I thought I would take this as a great opportunity to point out another application of capacitors. If I kind of show you a picture from your book, your author does a good job of showing you a keyboard, or the inner workings of a keyboard. They happen to be the letter B, but what happens when you're typing on a keyboard and you push down on the letter B? How does the computer know you've pushed on the letter B? Well, below it is a capacitor. And your pushing squeezes that plate together. As you squeeze that plate together, just like this one. Now, this one wasn't actually hooked to a battery already, but let's say it was already hooked to the battery, but had the 2 microfarads, you would have 200 microcoulombs of charge on there. And so as soon as you tap on that key, they get closer, maybe by a factor of 2, then charge is going to flow onto that capacitor. And then some circuitry in there picks that up and says, whoa, 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 current flowed. It flowed onto this key. That key represents a B. Display a B on the keyboard. And so each one has a slight variation. A lot of pressure and motion sensors are done this way. If you went into probably almost every fire station here in Santa Barbara, you would find these little sensors. They're capacitors. They're put in there by Caltech and the U.S. Geological Survey, but they want to know if there's movement of the Earth. And so they go into fire stations, they set them in there, and if the Earth moves, then the separation between the plates change. As the separation changes, they pick up a voltage. They send that by radio signal to Caltech, and they say, oh yeah, there was an earthquake in the Santa Barbara Channel this morning, a 3.1 earthquake. We got some shaking over in the Goleta Fire Department, or the Santa Barbara and the Carp Fire Department, and we picked all that up. And so motion sensors, pressure sensors, in this case, keyboard sensors, or how does that work? I touch it, yay! And things change. Why?
2 electromagnetic fields making a capacitor inside.
It's got little charges on it. What happens when I touch it? Oh, I didn't want to open that up. Yeah, the charge flows off at that point onto me. I'm making a bigger capacitor. The amount of charge changes. And the wires that go across this way and this way pick that up and say, oh, somebody's touching the screen. You ever try to touch it with a piece of plastic like a pen? Now, not the pointy edge. I don't want you to break your glass, but you touch it with this. It doesn't work. It needs your capacitance. It needs the charge to flow onto you. It's picking up the difference in that capacitance.
So if you touch it with a conductor, it will work.
Yeah, and you can buy those pins that use it. Now, it's nothing more than a metal pin with kind of a rounded ball, so it's not sharp and breaks your glass or scratches it. And it's conducting, and you're going to hold it. So by the time you touch it, it will flow onto the pen and onto you. And so you've got those little...
Why do you have those plastic black ball on them? Most of them, like the old ones, they just have the little plastic black ball on the bottom or something. I'm sure you don't have one.
It's not, yeah, but it's not plastic.
No.
Yeah, now,
Yeah, no,
the stylus. You sure it's plastic?
Or, not, maybe not plastic, but it's not metal. It's called a capacitive.
Yeah, my guess is it is conductive in some way. Now, with that said, I should be careful, but I think all the iPads and the iPhones work with the capacitance, but you can make it, the older ones made it resistive. And what they would do is put resistors between 2 pieces of glass, and as you pressed on them, you changed the resistance. So then it was just pressure sensitive. So some of them are pressure sensitive, but you can usually tell if you push it with a non-conducting, if it doesn't register, it's not pressure sensitive, it is capacitance sensitive. And some of the newer ones are using an ultrasonic wave across the top and the bottom. And as you put your finger in there, you disturb the wave, and it knows where the wave was disturbed based on the reflection. But those are really expensive, so that's real sensitive. So again, I don't think the phones are doing that quite yet. That'll be the next generation. Yeah. So, different materials. Anyways, sidetracked a little there, but I thought you'd like to get the idea of a good use for the capacitors, and these pressure sensors and these motion sensors are a good place, the keyboards. Well,
Works, but it's
let's go back then to finishing this, because here's B. B is going to make you think a little bit, not only about 121, but also a little bit about electric fields. I like the second part of B. What is the spring constant of each spring?
Oh, the force.
Okay, so as these things are being pulled in, maybe I'll draw, here is before and here is after. Here is before, here is after. Now that I've actually built up a set of charges in here, those have pulled in, right? And of course, you remember the force from a spring. What is it? Yeah, Kx, right? That's the magnitude. I know there's a minus there, but let's just talk magnitude. It's Kx. What's K? Spring constant. That's what they're after. What's X? Yeah, the distance you stretched it in. So in our case, how much did we stretch it in?
2 millimeters each. 2 millimeters each.
All right. So I'm going to put a 2, not a 4. Right? Did you catch that? Right? One spring moved in. So if I'm looking at the force from one spring, if I'm looking at the force, say, on this plate from this spring, didn't this spring only stretch 2 millimeters? The other one pulled in, sure. But if I'm trying to find the spring constant on this spring, what I need to know is that the forces are balanced at this point. That is, the force from the spring pulling it to the right is balanced by the electrical force pulling it to the left. And so it is only one spring touching here, and it stretched only a distance of 2 millimeters. Don't miss that. All right, I'll keep going. How do I get the electrical force?
Q times E.
Okay, Q times the electric field.
But wait, didn't the one thinking about like half QE because one plate only reacts to the other and not reacts to itself?
All right, I'm glad you say that. So what's Q?
400.
Yeah, we just did that one, right? All right, so this is 400 microcoulombs. What's E?
Gaussian surface.
Right? There's our change in voltage. So in a parallel plate, it's fairly simple, isn't it? The change in voltage divided by the distance, doesn't that give you the electric field? Right? Because the electric field's just a constant, so you can just do electric field times distance. And don't we know the voltage? Isn't the voltage 100 volts? Is the distance 2? 8? 4? 16? No one's going with 16, huh? 0.004 meters? Anything else? Well, that is the derivative of the potential. Yeah, right? That's how I got electric field. Electric field is undoing the integral. But I'm missing something important here. Half the electric field. Why? Right. The idea when we did forces was it's the charge on this plate times the electric field created from the other plate. This right here is the total electric field in between them. The total electric field is created by the two plates. So what I want is the charge on one plate times the electric field that is created by the other plate, which is half of the total because I've got two plates. And now I can find the constant K. Yeah.
Can you do also like 1/2 CV squared equals AX squared? CFG squared. Just do it.
No. Let me write that down. Would you say 1/2?
CV squared for the energy that's in the capacitor.
Okay, that's the energy in the capacitor. Yeah, you see it now, right? That's the energy of the capacitor. And you were about to say you want to set it equal to the energy stored in the spring. No, because the energy in the capacitor is not stored in the spring. It's stored in the electric field that's between the plates. Yeah. Yeah. But good. All right. So, no problem, right? You guys are more than ready for the test, right? Yeah.
When the two plates were originally 8 millimeters apart,
Yeah.
were the springs in what natural position?
Oh, yeah.
So there was no charge at all built up.
Yeah, and they did say that much. If you go back to 30, they say the circuit consists of two identical parallel plates connected to identical springs to a 100-volt battery with the switch open. The plates are uncharged. Yeah. And I'll take by that then the springs were at their natural length. Yeah. All right, let's try this one then. How about, let's see, I got the next one here is, 49 would be a good one. Where's my rag? Uh, 49 says we have a 2 nanofarad parallel plate capacitor, and it is charged to an initial potential voltage of 100 volts. And then it is isolated. There is a dielectric material between the two plates. It is mica, which has a dielectric constant of 5. Now, they don't have a picture of this one, but it's why I brought this out here. So here's my parallel plate capacitor. They're probably kind of close together like this. They have a dielectric material between them. I just have this vinyl, but they said it was mica in there. And then they hooked it to their power supply. So I take a couple wires, I hook it to my power supply. All right. So here's the picture. So far, so good? Because follow this carefully. A 2 nanofarad parallel plate capacitor is initially charged to 100 volts. It is then isolated. Okay, so what do we mean there? Yeah, so we now disconnect it. And then it goes on to say, you take this out. Anything happen? A, how much work is required to withdraw the mica? Does it take any effort to pull that out?
Yes, it does. Because there's a field on it.
And so if we come back to our picture here, when we drew our parallel plate capacitors, this material inside, as you might recall, decreased the electric field because the molecules in there got polarized. And what happened is this side became slightly a positive net effect, and that had a slight negative net effect. And so as you go to pull this out, if you kind of took an aerial view of this plate is negative, this plate is positive. If I have it half pulled out or something, with a bunch of positives here and a bunch of negatives here, isn't there an interaction between these? There is an electrical force holding that in. So when I go to pull this out, don't I have to do some work? And that's the question. How much work do I have to do? Well, maybe we should start here. How much energy was in this capacitor before I pulled it out? Now I forget the voltage on this thing. What was it, 100 volts? Yeah, 100 volts. So we're going to charge it up to 100 volts. But if I put here a 1/2 CV squared, then I have a 1/2. My C is 2 nanofarads. My voltage is 100 volts. Oh, nano. 100 squared is 10,000 nanojoules. Okay, so I got 10,000 nanojoules of energy stored in that capacitor, at least before I pulled it out. How much energy do I have after I pull it out? Did anything change? Did the capacitance change? It did, didn't it? Wasn't that the whole point of the dielectric? That if you pulled on something, or not pulled, excuse me, if you had the material in there, it would change the electric field, and the capacitance would increase as you put the material in, decrease as you took it out. So now that I've taken it completely out, and this picture doesn't show it completely out, so maybe I'll draw it again. And so here it is completely out. What's the capacitance now? Yeah, the dielectric constant was 5. And so this capacitance, which was 2 nanofarads, has now been reduced by a factor of 5. And so it is 0.4 nanofarads. So yeah, the capacitance has changed.
How did you get the factor?
They told me the dielectric constant was 5. They told me what it was. Okay.
We're assuming it goes out in free space then?
Yeah, so remember the capacitance, and they don't say it's a parallel plate one. But it doesn't matter whether it's parallel plate or not. What I wrote was the old capacitance, the capacitance with just air or nothing in there, free space, would then be increased by this factor of kappa, because the electric field was reduced by that factor of kappa. And so in this case, as you pull it out, you go from a big capacitance to a small capacitance. And the reduction is that kappa. So yes, I have a lower capacitance. Anything else change? How about the voltage? And really what I should ask, so that you'll get the whole idea of science, is you shouldn't necessarily be asking what changes, it's what doesn't change. What is consistent? That's why we have conservation of momentum. That's why we have conservation of energy. That's why we have conservation of angular momentum. That's why we have Newton's third law. What doesn't change? That makes life so much easier to focus on what is consistent from step to step to step in every problem. So I should ask Not what changes so much as what didn't change as I pulled that out. The key is the charge. What I know here is that I originally put a charge on here. Conservation of charge means that stuff can't go anywhere, and so as I'm pulling it out, I still have that same amount of charge. I haven't calculated it here, but maybe I should have back here. Back here in this initial step, I probably should have said, what is the initial amount of charge on this parallel plate capacitor? And it was 2 nanofarads before I pulled it out, and we had charged it up to 100 volts. Nano. Having a hard time with that nano today. And that is 200 nanocoulombs of charge that are on those plates. And while that's important is capacitance, voltage equals charge. If you just told me that the capacitance went down by a factor of 5, then what are you telling me about the voltage? If the charge isn't going to change, the voltage goes up by a factor of 5. And so this V goes from 100 to 500 volts. There's an increase in voltage.
But as we take the, the isolating
Yeah,
material out,
dielectric.
yeah, don't we like take off some of the charge? 'Cause
Well, in a perfect world, I'm saying no. In a perfect world, this is an insulator. The charges are on the conductor, and so as I pull it out, those stay there. They don't come out with my material. Okay, no charges ever get on my material. Remember in this picture, these charges in this picture are not representing charges that come from our plates. These are representing charges that were in the material to begin with. Okay? But there's, I think, maybe a little bit of surprising, and part of the reason I picked this problem is you got to figure out what doesn't change, and you might be surprised that the voltage did change. Some of you gave me the same look you gave me when I hooked up the 2 capacitors and closed them. We didn't end up with half the voltage. We ended up with 13.3. We don't end up with the same voltage. We end up with a lot higher voltage. So maybe we should address that. Why do we get a much higher voltage? Yeah, you could say it in 2 ways. Some of you are seeing it right away. The voltage is the electric field times the distance between this parallel plate. And when we had our dielectric material in there, the electric field was a lot smaller. That's what the dielectric material did. And as soon as you pull that out of the way, the electric field goes back up to how high it would have been had there never been any dielectric material in here. And so this electric field goes up by a factor of 5, which of course means the voltage will go up by a factor of 5. So that alone means I'm not surprised that the voltage went up. The other part of this is, earlier on I said it's going to take some effort for you to pull this out. As you are sitting here struggling to pull this out, you are doing work. That's why there's going to be more energy and more voltage in the capacitor. Your work is creating electrical energy in the process of pulling it out here. And so that's important as we come over here and say, let's calculate the energy now. The energy is 1/2 CV squared. This capacitor went down by a factor of 5. The voltage, as we just said, goes up by a factor of 5. Squared. That's 25. And that together means the total energy should have gone up by a factor of 5 as you pull this thing out. I'll put in the numbers here, but what I have is 1/2 0.4 nanofarads, voltage 500 volts squared. And if I put those in, hopefully you will see a number that is 5 times bigger than the energy we had before. So 0.5 times 0.4 times 500 squared gives me 50 5,000 nanojoules. And so sure enough, I've got 5 times more energy now than I had before. And of course that extra energy came from me pulling it, so I can answer the question now, how much work did I do? 40,000 nanojoules, that's where it came from. I did work on it. There was an electrical force pulling it, and I yanked it out of there. That energy showed up somewhere. It showed up in the electric field, the energy stored in the capacitor. Yeah.
What happens if you combine that with the previous problem where there's also a spring? Is that something that we can solve?
I'm not sure I'm quite...
Like the previous problem, how there's a spring, right?
Oh, you want to put a spring on here?
Like, what if you combine it with that? Is that something that we can still solve? Or is that,
I'll say yes, depending on how it's laid out. But yeah, we could put a spring on there and then do the same thing. We could pull this out with a spring, and then they get a little bit closer. And then not only does the capacitance first decrease because we pulled it out, but now the capacitance increases because they get closer together. Well, then if we left it hooked up to the charge, now we have a different problem. I mean, by the way, I should point out, what would have happened if this had remained connected to our 100-volt power supply?
Right back into the voltage supply.
Right. In that case, we would not have had this statement that says the charge remains constant. We would have said the voltage remains constant. And so as our capacitance went down by a factor of 5, our voltage remaining the same, the charge on the plates would have gone down. So what would have happened is charge would have migrated back from the plates back into the power supply. You've given them a different option, a different set of physics, so a different result takes place. Can the charges move or can they not? When it was isolated, they couldn't move. So what changed was the voltage and not the charge. If you left it hooked to the power supply, then the voltage can't change. The charge can, though, as it flows back in and essentially is recharging the battery. You're forcing the charges back into the battery. Okay. Well, I wanted to give you a bigger hint than the time I have left myself, bummer, for number 60. But 60 can be brutal. Let me help you set it up. I've only got a couple minutes here. I'll draw the picture here. Maybe I'll backtrack to a simple picture. A simpler picture. They show in some of the example problems. Good example using the capacitors. A little stud finder is a nice one. You put the positive, you put the negative. The electric field is created through here. And as you move this along the outside of the wall, here's the dry wall. If there's anything behind there, you're going to change the electric field because of the dielectric. And so as this thing moves along, you could detect things that are behind. They affect the electric field. And so the charge on that plate changes. Hence, there's a recording that when this machine was over here, there was open space. Now you move it to here, there is something else. And if this is a house, it would be a stud. And you move it along. Oh, there's the stud. That's where I'm going to hang my bike rack from there. And so I don't want to put it on the drywall. I want to find the stud, taking advantage of the capacitance. But this is probably a good picture to look at. What if we were to fill a capacitor partway up with a dielectric instead of all the way up? Yeah, and the best way to look at this is 2 capacitors in series. And say, all right, the total capacitance is number 1 and number 2. Thinking of this as a parallel plate, I would have mu naught times the area times the material, which is in this case kappa 1, and a thickness that your author writes, and I better go quick, as a fraction of d. So in other words, you had a capacitor that just had a thickness of D, and then you partially filled it. So this fraction may be like a third of the D. That would be the capacitance for number 1. The capacitance for number 2, now in this case, they didn't fill it with another dielectric. And so I'll change it a little bit, but let's say this area with another dielectric. So you have dielectric 1 and dielectric number 2. Again, you have the same basic idea where, since you filled it in this fashion, you have 2 capacitors in series. Fair enough? What if we switched it up? Instead of doing a partial fill like this, what if we did a partial fill like I thought we had a picture here. I'll draw one real quick. But what if we had instead a picture that had 2 parallel plates and we partially filled it this way?
Parallel?
Yeah, then they're just parallel, and it's an easier problem actually. It's C1 plus C2, and in this case it is kappa 1 epsilon fraction of the area divided by D, and the other one would be kappa 2 times 1 minus fraction of the area over D, right? So, you ready for a magenta one? What if we do that? No, you don't just add those 2 dielectric constants. My hint for you, now that we're out of time, think of this as a length of dx going back a width w. Don't I just have 2 capacitors in series where the area now is w times dx, right? If I work that thing around, I'm going to get the equivalent capacitance is a bunch of fractions with a dx. So then, if I add up a bunch, and I add across here 0 to L, wouldn't I get the capacitance of all of them in parallel? And so I'll start with series, small little capacitors, add them together in parallel, and get the total capacitance of this wedge shape. Good exercise in calculus. I don't know how practical it is, but good exercise in calculus.